In the last lecture, we have seen the formulation of the finite volume method for an irregular shaped domain. The idea was to divide the domain into small elements which may be tetrahedral or pyramidal or hexahedral elements, and integrate the governing equation written in the form of fluxes, where you have the advection and diffusion terms are brought together as divergence of flux, and we can evaluate this equation, the governing equation, by integrating over a particular cell. In the process, we convert the divergence operator into a surface integration over each side of the surface, so that we have an equation of this particular type: rho phi j n plus 1 minus rho phi j n divided by delta t times volume of the cell, and the net outgoing flux through all the faces is equal to the source term. And we made the point that we need to divide the control volume into small cells, and we need to find the volumes and the areas, and we saw how the volumes and areas could be determined from the coordinates of the vertices, and we also looked at evaluation of fluxes and how these could be evaluated consistently from the values of the cells which we are trying to determine. And in that sense, the formulation is complete except for generation of the points at which we would like to evaluate the solution. So that is part of the grid generation, and as part of the grid generation, we would like to find the nodes or the vertices and all the information about it. So we are going to look at methods for unstructured grid generation. When you look at grid generation, we need to have the basic theme incorporated in a procedure, which is to divide the computational domain into large number of small cells, and this is to be done in such a way that the cells do not overlap, they do not leave out any holes, that is, all the bounding surface should be covered without any gaps. At the same time, there should not be any overlaps, and the whole volume needs to be filled by the cells that we have chosen. So from the individual cells, we should be able to reconstruct the entire bounding surface and the entire volume through which the flow is flowing. So the computational domain must be recreatable from the cells that we subdivide into, and the cell should be roughly of similar size. We cannot have very large cells and very small cells in an arbitrary way, okay? And if they are not of the similar size, they should be in a distribution of our choice. For example, small cells in areas of large gradients of the variable that we are looking for is a very desirable feature of CFD, because if you want to resolve a large gradient, a steep gradient, you need to have large number of grid points, because the truncation error is proportional to delta x or delta x square times the gradient value. So if the gradient is large, the truncation error will be large. So you'd like to reduce the delta x there so as to reduce the overall truncation error. So we'd like to have good spacing, good cells. At the same time, when we are looking at large gradients, we'd like to resolve the flow better. So we'd like to have the small, only small cells in those regions. So in that sense, all these factors must be considered when we generate a grid. Generation of a grid for a fairly simple geometry that can be fit into a Cartesian coordinate system is not so very difficult. It can be done intuitively, it can be done by inspection, but when you have a more complicated domain, then we cannot do it in an arbitrary way, and we have to do it algorithmically. Okay. So grid generation is non-trivial for generic shapes, and one would have to have a generic approach for grid generation, not something that would work only for a certain number of shapes, certain types of shapes. Okay. So, just to see what the issues are in terms of grid generation, the major issues, consider this domain here that we have, which has these 5 surfaces. It is like a pentagon, not quite a regular pentagon, inside which you have another pentagon like this, and whatever is the domain in between is a computational domain. So, this looks very regular to me, but it is in a way non-trivial kind of thing, and it obviously cannot, these surfaces here cannot be represented in simple Cartesian meshes. And so, if you want to generate a domain like this, a grid for this, it is a 2D shape, and in such a way that we break it up into small number of triangular cells, and which when everything put together will make up the entire shape without leaving any holes. Then we need to first of all see the where we would like to have the boundary nodes. For example, we can put boundary nodes here over all the boundaries, and maybe on the interior also, and then we can try to put some internal nodes like this, and then we can join them to generate a grid like this. Okay. So, we are going for a given shape like this, we are going through these steps here to finally end up with something like this. We have got a triangulated mesh, and this whole domain is now decomposed into smaller triangular elements, and all of these put together will make up the entire shape, will fill the entire control volume, and every part of the boundary here, every part of this boundary and this boundary is part of, is the side of one of these triangles, and the whole of that boundary domain is put together in this. So, we would like to go from a shape like this, a computational domain like this, into a shape, a triangulation like this. Now, this is a very coarse grid, and we really cannot use it for CFD kind of solutions with any kind of accuracy, but the idea is to go from there to here, and here is where we have a grid which meets those kind of considerations, that all the boundaries are part of this grids, and the whole boundary is there, and all the computational domain is included as the area of the individual cells, and the sum of the areas of all the triangular cells is equal to the sum of the area of the computational domain. So, when you want to go from just a boundary into a triangulated mesh like this, then we would have 3 major steps to reach up to this particular point. First is fixing the boundary nodes, and second is fixing the interior nodes, and then third is triangulation. Okay. So, that is joining these individual things to make up a triangle. We may look at these as fairly simple to do, but one would have to take a lot of care in making sure that, for example, all these points are well distributed. So, what we will do in this lecture, given that grid generation is non-trivial, we will look at how to go from this domain shape into the stage where we can put the boundary nodes and the interior nodes, and then we look at triangulation in the next step, because that is definitely a non-trivial exercise. So, we are looking at fixing the boundary nodes and fixing the interior nodes. So, here what we have is a domain, and we also know the boundary condition, we also know the equation that needs to be solved, but how to fix a grid for this? That depends on number of factors. it depends on how at what stage of solution you are. If you are making a first cut solution, first time you are solving a problem, maybe it is a good idea to have a fairly coarse grid just to see that what kind of solution you get, and then where you think are what kind of flow is taking place. Is this the correct way to formulate the problem? Have you got all the boundary conditions? Have you got all the information that is needed for the solution? So you need to fix all those things and then maybe look for a final solution. So it would be a good idea to start with a coarse grid, and then you can refine it further and further. So when you are looking at coarse grid, how coarse it is? We are looking for a CFD solution. We are looking at solution of nonlinear equations and highly coupled equations. So we'd like to have good accuracy. It cannot be a few grid points so that we can get a quick solution. And so that is where we'd like to see what kind of flow scales we want to resolve. Okay. So that is one particular constraint. If you are looking at if you already are expecting certain features of the flow and these need to be resolved, then if there is a certain region in which you are expecting say a large velocity change, maybe 50% velocity change, then so that means that when you look at a velocity change, you are saying that at this point the velocity is here and at this point the velocity is here. You would like this velocity variation to be resolved. So that is, you would like to have a few grid points, maybe 3-4 grid points here, so that you can say velocity at this point is here, the velocity at this point is here, the velocity at this point is here, and when you join them you get this straight line. So the more steep the gradient is, the smaller will be the grid point. The more regular the variation is, the fewer the number of grid points. If you have a linear variation, then you need only 2 points, this point, the velocity at this point and the velocity at this point, to make up the straight line. But how do you know in somewhere in the interior you have a linear variation? You do not know. You would like it to come out of the solution as part of the solution. So you should have sufficient number of grid points to resolve velocity profiles that are going to be generated by the solution. So you should want to have a decent number of grid points. So based on for example, if this is the flow domain shape and if I am expecting some profile here, then I would like to have maybe 10 points in between. Okay. So if I am looking at 10 points, based on that I can say that I would like to have a grid spacing of so much. It is not possible in the general unstructured mesh to fix a uniform grid spacing which will work for all the cells, but there should be an estimate of the size of the cell. In this case we are looking at a triangular cell. What will be the side of the triangle, side length of the triangle that you are looking at. So that can be a beginning basis to fix your boundary points. Let us say that in this particular case I have taken a large size so as to make the solution clear, but this much variation, this much delta x is not such a good thing. So let us say that this is the size that you want to have. You start at some point in the boundary, you move along the boundary and then you move that much distance, say a small l, and then you fix the point here. You move another small l distance, you come here, and then you can keep on putting these markers along the boundary and say that this is where you want to have the cell. That is one possibility. For more complicated things, it may become you may need to think more imaginatively as to how you can fix this. For example, you can draw lines separated by that much distance and find out the intersection of these horizontal lines with the boundary points, and along that you can put. Okay. So or you can find out the distance from here along the boundary, and so in that way you can fix certain you can fix the boundary points. So, you fix the boundary points on all of these. Okay. So, now how do you fix the interior points? So, the interior points should be fixed in such a way that there are points all over the place. So, that is over the entire computational domain we should have those points, and these points cannot be in haphazard location. They should be roughly of equal distance from each other, and obviously they should not be very close to this to the surfaces, to the boundary surfaces, because if you had a point here and then if you joined it by like this to make a triangle, then you would have a highly distorted triangle, and something like that is not very desirable. So, you would like to have a method of placing the interior nodes in such a way that they are distributed all over the computational domain, and that there is a sufficient gap between the points and between the points and the boundary. Okay. So, with these kind of things it is possible to come up with a simple way of doing this nodalization, that is fixing the interior nodes. Okay. So, what we can do is that for a shape like this, you know the total maximum height and minimum height, and you have some characteristic distance that you would like to have, the small l that you would like to have between the grid points, which can be the estimated size of an equilateral triangle that you would like your triangular cell to be. So, with that thing, and starting with the bottommost point, you draw horizontal lines which are separated by the distance L. So, you have line AA, BB, CC and DD, EE, FF, GG, all these things are these kind of horizontal lines which are roughly spread set apart by a distance small l. Now, given this line, you can find out what is the where this line is intersecting the boundary. For example, this line A is intersecting the boundary at this point and at this point. Line BB is intersecting the boundary here and here. So, if you know the boundary equation, then if you know this equation, and you can find out where the point of intersection is. So, once you do that, then you are now in a position to see what is the length between the intersection which is part of the computational domain. For example, if I take this line here, this part from here to here is inside the computational domain, and this part is outside the computational domain. So, I can find out from this intersection what is the length of this line which lies inside the computational domain. Now, along this line I fix as many number of grid points as I need to have in order to have a separation distance of about L. So, for example, here along this line is this length is short, maybe I will have just 2 points here, two intervals here. Along this line I have wider width, so I can put one distance L, second distance L, third distance L, fourth distance L and fifth distance L. So, along this I can put 4 points and if I come to line DD, it is intersecting the boundary at point 1, point 2, point 3, point 4, okay, at 4 points, and out of this, when you have an even number of intersections like this, that means that if you have one internal space which is not part of the domain, here you have only this part is part of the computational domain and this part is part of the computational domain. You do not want to put any grid points outside the computational domain, because if you do that, if you have a grid point, it has to be connected to other grid points to make a triangle. So, if you have a grid point inside here, and then if I join it like this to make a triangle, then part of the triangulated domain lies outside the computational domain, and you will be violating the principle that when you put all the triangular tiles together, you should get exactly the area of the computational domain. Now you will be getting a bit higher. So, you have to make sure that you do not have any points outside this computational domain. So, you say that I take this length and then I put one point here to make it into two equal sides of roughly L, and here also I do this. So, I can continue like this, but if I look at point C here, then this is passing through this, okay, almost passing through like this, and so in such a case I can move it up or down slightly and then put the points here. So, in a case where I feel that the points are very close to existing points, then I can move the points up or down, because I know that it is not possible to get exactly the same length L all the time. It is okay to have sometimes maybe to have 0.7 L distance or 1.3 distance L distance. So, accordingly we have to move the interior points around after using this general guideline to place them inside. Okay. So, this is one simple way for a 2D case of fixing this kind of domain. You can also extend this logic to 3D, and then you can do this. So, in that sense, nodalization, which is the task of putting points inside the computational domain, so that all points are inside the computational domain and are spread throughout the computational domain, requires some estimation of the distance between the points that you would like to have. And once you have that kind of distance, then and once you have a representation of the boundaries and the boundary nodes, then you can go through this kind of exercise to get all the internal points. Okay. So, once you have all the internal points, you have got something like this. Now, the next task is to join these to form triangles. Okay. Now, joining this, it looks like a very trivial thing to do, but if you have to do it with your eyes closed, and if you have to if you know only the xy coordinates of this, then which one to join with what is something that needs to be determined. So, for example, if you join here like this, and then if you join this one like this, then you are overlapping. Okay. If you join this and if you join this, but do not join these two, then you have some area which is left out. And if by chance you join this, and then if you join this and this, there is again going to be some overlap. So, in that sense, there is possibility of overlap, there is a possibility of leaving out certain part of the domain, and there is also the desirable feature that if you are making into triangles, then you would like the triangles to be as equilateral as possible. We do not want to have two distorted triangles. So, these are the kind of constraints that are present when you are doing triangulation. So, we will look at triangulation in the next lecture. Okay. So, what we have done in this lecture is to understand what is there, what are the kind of issues that we have to face when you are doing unstructured grid generation. Given the fact that we have a domain which does not fit into a regular constant x, constant y kind of things, as shown here for this simple case, and given that there may not be any regularity in terms of this, you need to have some imaginative way of trying to put interior points throughout the domain in such a way that they are separated roughly by a distance, a desirable distance apart, and that they are there everywhere and only inside the computational domain and not external. And we also need to make sure that the entire boundary is completely divided into segments, and these segments are also such that there is a desirable distance between one segment and the next segment. So, with these kind of ideas we can do nodalization, and triangulation is something that we will see in the next lecture.